So, now let us come to this Thomson's tetrahedron. Now, again going back to our cube, this is the cube and these are the atoms. Now, we want to find all the possible 111 planes. So, this is one set of 111 plane, but and we are talking about types of family of 111 planes, not the same set of 111 planes. This is what we are talking is family of 111 planes. Okay. So, now this is another 111 plane. So, this is connecting all the 110, this is another 110. So, this forms another family of 111 plane. Now, again you connect these and you get another family of 111 plane, and if you look closely this and the line behind this also forms another set of FCC planes. So, this will become like this. So, we have 4 different 111 planes over here, and if you recall from our earlier lecture in the part 1 that FCC has 4 different possible 111 planes and of course their negatives. So, we have outlined all of these here. So, that is a very good thing. Now, inside the cube we have outlined all the 4 possible 111 plane, and we see that it forms like a tetrahedron. Now, we can take out the tetrahedron, it will look like this. So, this has 4 triangles, 1, 2, 1 on the back and 1 over here, and other unique features of this tetrahedron that it is equilateral. Another unique feature that all the edges that you see are actually along 110. So, even the directions, the edges are also telling us something about the possible Berger vector, the 110 direction, and we know that each 111 plane has 3 possible 110 direction, and thankfully for us each of these are triangle. So, and all these 3 are representing 110, 3 independent 110. So, this tetrahedron is very, you can say, gift for us in that we are able to see all the 111 planes, and the corners of this triangle are giving us the 110 directions. So, all the possible 111 planes, all the possible 110 directions in that particular plane can be identified using this tetrahedron. The tetrahedron that I drew over here is taking the full cell, but in reality what you need to draw, or because the Berger vector is equal to the closest packed direction. So, what you have to do is draw along the or join the corner atoms of the 4 nearest neighbors. So, here are the 4 atoms A, B, C, D, and you connect them, you get the same tetrahedron. There is no difference in the orientation etc., but this is a more accurate representation of where we are getting the tetrahedron from. So, because the edges represent here the equal to the Berger vector, the BD length, the AB length, they all represent the Berger vector. And if you look at it from the top, this is how the tetrahedron would look like. Now, you have the A, B, C, D corners, and these dotted lines represent another triangle. Now, here at this point let me introduce you to a similar thing that you can draw on your own, and thankfully to the internet there are several such possible tetrahedrons that you can download from the internet. So, but whenever you download from the internet, I request you to look at the accuracy. For example, if you are looking at the different vectors on a plane, make sure that all the planes, all the vectors do lie on the plane, because when I looked at some of the possible Thomson tetrahedron downloaded from the internet, there were some inaccuracies. So, just be careful about where you are downloading from and to cross check that everything that you have is right. So, now I will take this is I will just first make it like a tetrahedron. So, this is our tetrahedron, like I said, this has 4 triangles. Now, you can see 1, 2, 3 and the 4, and like here shown over here, I am putting it over here like this. So, you have the 3 the triangles, and when you are looking from the top, you can see the 3 triangles that you have drawn over here. So that these 3 triangles become the 3 triangles over here and the base triangle is over here. So this is the tetrahedron, and like I said that there are 4 sides to it and it represents all the possible 4 111 planes in a FCC system. And the edges that you see over here, they are, you remember, along the 110 direction. If you look over here, they are along the 110 direction. So, they represent the possible Berger vectors or the possible slip directions on each of these 111 planes. And if you accurately draw the x, y, z, you can identify what should be each of these, and like I said, this is also possible to download from internet. So, this is the Thomson tetrahedron that we are talking about. Okay, so before I get back, let me show you one of the possible thing that you can download from the internet. So, this is how it will look like. So, this is the Thomson tetrahedron, and over here now I will show on the screen you can see this big triangle. Over there are 4 smaller triangles, and here also I am showing on a paper printed something similar that was drawn here, and it has as you can see, it is a big triangle and it has 4 small triangles, and from this you can make the tetrahedron. You just fold it along the smaller triangle that you see over here, and when you connect it back you get the tetrahedron. So, this triangle and the tetrahedron are not different, it is just the 2D version of the tetrahedron, and we will come to more information about it later on, but let us now come to the triangle part over here. So, here each of these triangle you can mark a center. So, for the triangle just opposite to the A side, A corner, the center is marked as alpha. The center just lying opposite to the C corner is marked, actually it should be gamma, and the center just opposite to B should be marked beta. So, before I upload, so that you do not get confused, let me correct it here and now. So, this is how it should be, since it is opposite to C, the center should be marked as gamma, and opposite to A alpha, opposite to B it is beta, and opposite to D, which is just in the center, there will be on the top of this is the corner D and the bottom is the delta. So, this forms a tetrahedron, and these are some important points that we will talk about, and we will continue on this in a moment. So, coming back to our Thomson tetrahedron. So, this is the tetrahedron, and like I said that there are 4 triangles and the center of these triangles are marked by a Greek letter alpha, beta, gamma, delta, and these are unique, located at a unique position. Do not assume that alpha can be anywhere. Alpha will be just opposite to the point we have marked A. Similarly, beta will be marked just opposite to the point we have marked B. Gamma will be just opposite to C, and so on. Now, let us look at it over here. So, again you can see that A, B, C are over here. The way this has been folded or the way this has been drawn is that D would lie, when you fold along this A B, B C and C A, then D will, all the 3 D points will come together into one point. So, that becomes D. Now, you see this is the A point. So, the just opposite to this will lie this triangle, and the center of this will be marked as alpha. Now, this is B. So, just opposite to this is beta, this is D over all the corners. So, the delta is in the center of this triangle, and so the C, this is the gamma. So, now these are important points A, B, B, C, C, D, D, A and alpha, beta, gamma, delta. Now, what is the importance? The importance is that the full dislocations over here can be represented, which is the Berger vector equal to like we said these are the edges. So, in terms of A B B C we can write it as A B B C C A D A D B D C. So, these 6 represent the Berger vector for a full dislocation. On the other hand, partial dislocations which have the Berger vector of the type A by 6 1 1 2 are basically line from corner to center of that particular plane. So, if this is the corner, then to the center, this line represents the Berger vector of a partial dislocation, and for each of these you can see there will be 3 different and unique partial Berger vectors. So, if we are talking about the A corner, then A corner can have for A gamma, A delta, A beta. So, this will be A beta, A gamma, A delta. For B, B alpha, B beta will not exist, B gamma will exist and B delta. For C, C alpha, C beta and C gamma will not exist, C delta will exist. So, of all the 4 possible combinations for each of these corners, one is missing. Now, you have to see what is the pattern. It is not very difficult to recognize. So, what you see is that here A alpha is missing, here B beta is missing, here C gamma is missing and here D delta is missing. Okay. And when you look at it, these 4 vectors are actually very different in magnitude compared to these 3, these 9 that we have over here, the 12 over we have. So, these are a different set of vectors, we will come to that in a moment, and these are a different set of vectors which we have described here, and these are nothing but the partial, like we said, partial dislocations, and they have the vector of the kind A by 6 1 1 2. Now, using this notation there is still another advantage. Let me show you that you can describe the dissociation of a full dislocation into the partials using this notation. Now, what is that notation? Let us see. So, if you have the full dislocation, let me use a different color again. If you have a full, right, like we said, AB will represent a full dislocation. Now, this AB can dissociate into, now this you can see this is AB. Now, if it will dissociate, it will either dissociate on this plane or this plane. So, there are 2 possibilities, and for each full dislocation it lies on 2 planes, and similarly it can dissociate onto 2 planes. Here AB can dissociate in ABD plane or it can dissociate into ABC plane. We will assume that we are dissociating into ABC plane. Now, what are the possible Berger vectors for the partial dislocation? A delta and delta B. So, this becomes A delta plus delta B, and this represents the dissociation of a full dislocation into partials, and this is happening on ABC. Now, similarly it could have dissociated the same Berger vector or the same slipped vector could have dissociated on a ABD plane, and in the ABD plane this is your one partial Berger vector, this is another partial Berger vector. So, here AB would have dissociated as A gamma plus gamma B, therefore, and this is on the ABD plane. So, this is another advantage of using these notations, and whenever you are using these notations, you have to be also careful when I write A gamma and gamma B. So, A gamma is a vector like this and gamma B is the vector like this. Now, if you have already given the vector like this, which is 1 bar 2 bar 1, it means it is going in this direction. So, when I dissociate AB, then I must write the negative of this, which will be, so if I want to describe this, then it will become bar 1 1 0, I will have to take negative. So, this is A by 2 and this will dissociate into A by 6, this is along the direction, right direction. So, I will take it as it is. So, this becomes bar 2 1 bar 1 plus I have to take negative of this again, because it is showing in this direction, plus A by 6 bar 1 bar 2, sorry not bar 2, this is 2 1. So, this is the same reaction as this one. Now, using the vector notation, now is here using just the delta notation or the ABCD notation. So, now for a few things let us look at it. This is lying on a bar 1 plane. So, if you take the dot product of any of these 3 vectors, you would see that it indeed comes to 0, which means that all these 3 are lying on bar 1 plane. That is one thing. Second, when you add these, you must get onto the left hand side. For example, if you add this, this is bar 2 bar 1, so this becomes minus 3, this becomes 2 plus 1 3, this is minus 1 and plus 1 0. So, this becomes bar 3 3 0 and this is a by 6. So, 3 and 6 cancel out. So, it becomes a by 2 bar 1 1 0 and this is what we have on left hand side. So, this again does indeed break into the way we have expected. This becomes this is the sum of these two, and it should be, because that is how these have been drawn. But if you had taken it as it is without changing the sign of this vector, then it would have been erroneous and you may have ended up getting wrong results. So, once you have the Thomson tetrahedron, you have to select the direction carefully and appropriately used in your dissociation reactions. Now, that we are talking about the partial dislocations, let me also add another type of partial reaction or the partial dislocations, which is called Frank partial dislocation. Now, this is also H particular, only the H type of dislocation. And how are their Berger vectors? Now, here is where we will come back to our original notation of using partial dislocation vectors, and where we excluded just 4 of those possibilities: A alpha, B beta, C gamma, D delta. Now, these Berger vector, if you look carefully, they have the Berger vector of the order A by 3 1 1 1, not, remember, for the usual partial dislocation that we talked about, which move away and create the stacking fault region, that is of the type A by 6 1 1 2, but this is not A by 6 1 1 2. So, this is completely different in magnitude, and that is why we have not included it here, but we include it in a, or this is a different type of partial Berger vector, and it is called Frank partial dislocation. Why it is different, we will come to that in a moment, but for now this is possible in 4 different configurations, or there are 4 different vectors which have this type of Berger vectors, and these are, you guessed it right, A alpha, B beta, C gamma and D delta. So, if you look at the Berger vectors, okay, let us get back to here, and you have alpha here and A over here. So, there will be in the shape of a triangle, or if I go back even further. So, if I go back to here, D delta is a line going from the top of this tetrahedron to the center of this triangle. Similarly, A alpha is the center from here to over here. So, this is a line lying somewhere in between the tetrahedron. This is what is called the Frank partial dislocation. So, A alpha, B beta, C gamma and D delta are the Berger vectors of this kind. Now, another thing is that you will note that this does not, I will say call it BF to differentiate, BF does not lie in 1 1 1. Okay. So, this is a direction 1 1 1. So, it will always be normal to one of the 1 1 1 planes, and the 1 1 1 planes normal do not lie on the 1 1 1 any of the 1 1 1 planes, and therefore, BF also does not lie on any of the 1 1 1 plane. But for a dislocation to glide, we know that it must lie on 1 1 1 plane. Therefore, what does it imply? Hence, this cannot glide. implies sessile. Okay. In dislocation terms, whenever a dislocation cannot glide, we call it sessile dislocation. Sessile is nothing but it means that it cannot glide. Now, coming back to here, the other dislocations that we talked about, they can be described, they are described, this is frank partial dislocation. The others that we described earlier were Shockley dislocations, Shockley partials, like the ones that we said. These are Shockley partials, and these are glacial, meaning these can easily glide, because you know, remember they are on the 111 plane. However, keep one thing in mind, that frank partials, although they cannot glide, but they can certainly climb. Meaning climb is possible for even the frank partial. I am not saying that these will not climb, these will also climb. So, can also climb, but of course, the glide is the more easy phenomena. So, it will prefer to glide unless it is facing some obstruction. So, these are the important points with respect to the partial dislocations. Now, the next topic that we will touch in the next class is about a dislocation lock that can form because of the interaction of dislocations on different planes, and this kind of lock can also form where even if the dislocations dissociate into partials. So, we will come back and meet in the next class. Thanks.